Okay, welcome back to a new Geant4 tutorial. In this video, I would like to continue where we stopped last time with creating our first project by now filling it with life, so to say. So what we will do, we will add a few things that are necessary for every Geant4 application. We will add a physics list, we will add a detector construction, and we will add a particle gun. And with all that, then at the end, we will be able to create our first particle interactions with matter. So before we can do this, we have to add a few things, and for this reason we will go back to our CMakeLists.txt, and where we said that find package Geant4 is required, we have to add two more things. We have to add UI all and vis all for user interaction and visualization. This is very important. If you are not doing that, we will receive some error messages after that. Okay, so now we will first start with our physics list, because this is the easiest part. So now what we will do, we will create a new folder here in our base folder. And as I said last time, we call that src for source code. And we also create another folder in our base folder, which is called include, which includes then later all the header files. So now in this include folder, we create here a file which is called PM, I call it, for physics matters, but of course you can also choose any other name, PM physics list.hh. Yeah, so this is our header file for the physics lists. And then we have to protect this header file to make sure that we are not implementing it several times, which means that we have to use the standard C++ trick. If not defined, PM physics lists _hh, but of course you can also choose any other definition here. It's not necessary that you choose the same. The most important thing is only that here you use the same. Yeah, physics lists _hh, and here we have to use and if. And we have to include our standard G4 V modular physics list.hh. This is very important, yeah. And we just choose in the beginning. Of course, we will later use many other physics lists, but for the time being, we will use simply the G4 EM standard physics.hh, which is the standard physics list for electromagnetic interactions. So now we can here define our class. So what we can write, class PM physics list, and then we have to inherit from the G4V modular physics list that we have included. And this is everything what we have to do in principle. Now we have to create only the constructor, which we can define like that, and our destructor PM physics lists, which we can do in the following. Here we need to add a semicolon, and then in principle everything should be completed. Now we go to our source folder here, and we create here a file which we call PM physics list.cc, which will be our source file. And the only thing which we have to do here is we have to include our PM physics list.hh, and then we have to define our constructor physics list PM physics list. Of course, we could also do this directly in our header file because there is not so much included, but I would like to separate this a little bit to make sure that later we will not fall into trouble and to make it a little bit more beautiful. So as I said, we just want to use electromagnetic physics. So we have to register physics here. And this is our G4EM standard physics that we have included as well. And then at the end, we have to also define our constructor. which will be empty. Yeah, there's nothing which we have to delete actually. And here I made a typing mistake. There should be an S. And now in principle everything should be okay. Whenever we add something, we can test whether it works. So in our terminal, we go into our build folder and we have to write now CMake ... to make sure that it finds all header and C files. And then we can build that. And as long as we are not getting any error message, we are fine to go. Now we have to register this physics list in our main file. So we have to go back to our sim.cc. And here we have to go below the line where we defined our run manager. And there I will write a comment here, physics list. And there I will take our run manager and write here or use this member function set user initialization. And then I will write here new PM physics list. And of course it will not find that because we have to include this here as well. Yeah? So we have to write here include PM physics list dot HH. And now again here we have to close our parentheses. And now again we included something. So I would like to compile our program to see whether we have done everything correctly. Yeah, it's always good to let the compiler tell us if we did something wrong. Everything seems to be okay until now. Now in the next step, we have to create another file in our include folder, which we call now PM physics matters detector construction.hh. And this will be our detector geometry. Yeah, so we will also use our same trick that we used before. If not defined, PM detector construction HH, then define the same one, and otherwise and if, and otherwise if not defined, then include. And now we have to use our G4V user detector construction. So this is the main class from which we inherit now. And what we later use is just a simple box for the world volume. So we have to include our G4 box HH. And we have to include a few more files related to the volume. So in Geant4 we have a solid volume, which can be, for example, a box. Then we have a logical volume and a physical volume. And what it means I will explain after that a little bit more in detail when we come to this. But now at the moment we will just include these header files. So logical volume HH, and the next one will be G4V physical volume HH, and then we will include G4PV placement.hh, and also we need later to define some material. So here we include our G4 material HH. For this material, in order to define this, we also need this G4 NIST manager. And here you can see why it's important to include our headers, our header path into this Visual Studio Code, as we have done last time, because now we can use auto-completion all the time. So now include G4 system of units HH is very important, because we have to use units like meter, mega electron volt, and they are all stored in this system of units, as well as in our G4 units table HH. So all that we need. And now finally we can define our class PM detector construction, we will call that. And as I said, we have to inherit from G4V user detector construction. And then here we have to define our public constructor, which would be PM detector construction. It can be, it doesn't take any parameter. And then our destructor, this has to be a virtual function because it is already defined in this function, in the class that we inherit from. So we have to write virtual before. and then PM detector construction as we have done before. And then another one which is important, which will also be a virtual function because it's defined there and we have to override it. And this is our G4V physical volume. And this is our main function which takes over the construction of our detector. Yeah, so we have to, the return value is a G4 physical volume. And yeah, we just have to point to that. So this is actually everything which we have to write into our header file. And here we need a semicolon in order to, yeah, to close our class. Yeah, and now we go to our source folder, and there we also create a file called pmDetectorConstruction.cc. And yeah, then we have to include our pmDetectorConstruction.hh. And then we have to define our constructor here, pmDetectorConstruction, pmDetectorConstruction, and just like that. And to make it a little bit shorter, we can just copy and paste this part here and make our destructor from that. Okay, now what we have to do is to define our G4V physical volume. And then we have to write here our PM detector construction, our class, and our function construct, as I explained before, our main function. So before we come to the definition of the volumes, I would like to set one variable, and this is a Boolean. And this we call check overlaps. Yeah, because in Geant4 it is important that our volumes do not overlap. As soon as volumes overlap, Geant4 cannot calculate the boundaries correctly, and then the physics will go completely wrong. Therefore, it's important that volumes are separated from each other, and there is a overlap check included in Geant4, and we can activate this or deactivate this depending on what we want, and I would like to activate that. So now we have our G4 NIST manager, as I explained before, which includes several materials. So we now take we create an instance of this manager, so we can write G4 NIST manager instance. And then we can define a material, which will be our world material. We call it world mat. This is taken as NIST find or build material. And then Geant4 has already included some of these materials in our NIST manager. So in this case, we can simply write G4 air. And in this case, then Geant4 knows how air looks like and then applies this air to our world volume. And then we can now finally define our volumes. So first I would like to define the size of our world volume, which is 1 meter. Yeah, so this meter is a unit, and we can only use this because we included our unit table before. And then our Y world we also want to define, which would be 1 meter. And then we also need our Z world, which is equal to 1 meter. So our world volume should be a box. Therefore, what we can do, we can write here G4 box solid world. And as I said, we have solid, logical, and physical volumes. And solid is the definition of the shape. Yeah? So now we have a box. This is our solid volume. And here we have to write new G4 box. And then we have to give it a name. And I always recommend to choose the same name as the name of our object, just to make sure that we at the end do not mix something up. And then we have to define, depending on which volume we have to define certain parameters. So a G4 box takes over 3 parameters, the length, the height, and the width. So our length is given in x direction as x world, but because it always takes half of the length, width, and the height, yeah, we have to multiply it with 0.5, yeah, which is actually half a meter, but then it extends it to 2 times this half length and this is then the length of our volume. So in this case, we always have to make sure that we multiply it with a factor of 0.5. And then the same for the y-axis, y world, and the same for the z-axis, z world. So depending how you define it, you have one is the length, one is the height, and one is the width. So now we have defined our solid volume. So now we can actually define our logical volume. And you can see after I saved the file, it also takes the information from this header file here. And now we can use autocompletion again. So G for logical volume, and then logic world, new G for logical volume. And now we have to hand over our solid volume, which is solid world. And we have to hand over our material, which is world mud. And we have to give it a name, which is logic world. Again, I would recommend to use the same name as we have used for the object. And now it also becomes clear what a logical volume is. The logical volume is actually taking over this solid volume and applies a material to that, which is in this case world mud. Okay, and now we can define our physical volume. Yeah, G for V physical volume, and this we call phys world. And now we actually have to place this into our world, which means we have to write here new G for PV placement. And then first we have to think whether we have to apply any rotation. In this case, we do not. Later I will show you examples where we can do that, but for the time being, we assume that we don't have any rotation. So we can simply insert a 0 here. And then for the position, x, y, z position, we can use a G43 vector, which is a class that takes in the constructor 3 components, yeah, x, y, z. So we can write here 0, 0, 0, because we want that our world volume appears in the center of the coordinate system. And then we have to hand over the logic volume, so which is in this case logic world. And then we have to give it a name, so we call it phys world. And then we have to tell Geant4 if there is any mother volume. Yeah, so this volume could be inside another mother volume as a daughter volume, but since this is our world volume, there's no volume around it, so we can simply write here 0. And then we can write here false in the next one, because we don't want to use it as a Boolean. And then we have to define our copy number, because we can have several physical volumes from one logical volume. So in this case, we have only one, therefore we can just write 0 here. And then in the last step, I would like to insert our check overlaps variable to make sure that our overlaps are counted in the future. Now this is done, and we have actually completed now our construct function. The only thing which we have to do now, we have to return, of course, our physical volume, which means we have to write here now return phys world. So now we can test this and write here CMake ... again in our build folder and write make, and then we can see if we get any error message. Yeah, so as you can see in our header file, I did a small typing mistake. So instead of construction, it should be only construct. And now we do not see any further mistake here. We can try to build it again. And this time we do not receive any error message, which means that now everything is fine. Yeah, and now we go back to our main file sim.cc, and again we include here our pm detector construction.hh. And now we can also include our detector construction here. So instead of physics list, we write here detector construction, and our set user initialization we can still keep as a member function, but here we have to write new pm detector construction. And now in the last step, we have to actually create our primary particle generator. So I will create here again a new file, which I call pm primary generator.hh. And we will do the same as before. If not defined, pm primary generator underscore hh, define pm primary generator hh, and here we can write end if, and now we can define our class pm primary generator. And now before we have to continue, we have to add a few more header files. So we have to write here G4V user primary generator action.hh. And another one which we have to include is G4 particle definition. And this is very important for having access to definitions of particles like electrons, protons, and so on. Then we also have to include our G4 particle gun, and this class is important for shooting particles later. Then another one which we have to include is G4 particle table, and again G4 system of units is important to make sure that we can use standard units. Okay, now we can then inherit from our class G4V user primary generator action. And then again, we have to define a constructor and destructor. So we will write here public pm primary generator and pm primary generator. And yeah, here we also have to override a function that already exists, and this is called generate primaries, and this takes over an object from the so-called G4 event. Yeah, later we will see what this actually means. And then we also have to, or we should maybe define here a private member variable or private member object, which is G4 particle gun f particle gun. And again, we have to end this with a semicolon. So now we have to go again to our source folder and create a new file, which we now call pm primary generator.cc. And then we have to include, of course, our primary pm primary generator.hh file. And then primary generator pm primary generator for our constructor. And in this constructor, this will now not be empty. This will be now filled with a few things. So we have defined already our object f particle gun. So this we will now use by writing equals to new G4 particle gun. Yeah, and here we have to insert number 1 to make sure that we have only one particle per event. Later we can also change this, but for the time being I would like to keep it like that. And then I would like to first define the position of the particle. So for this I create 3 doubles, x equal to 0, y equal to 0, and z equal to 0. We can now write also times meter here in this case, which does not make any sense because 0 is 0, but we could do this just for consistency. And then we can here write our G43 vector. So we create a position vector with these components x, y, z that we have defined before. And then also what we have to define is a particle direction. Yeah. So again, I would like to create a few doubles, px equal to 0, g4 double py 0, and g4 double pz equal to 0, p's for momentum. And then I would like to again define a vector which I call mom for momentum, px, py, and pz. So, and then the particle type is very important to define. So we can now write here a comment, particle type, and there we can take this particle type from the particle table from which we create an object called particle table. And this is actually this we can actually take from that class G4 particle table, and there is a function included called get particle table, and this we will use now in order to define our particle. So what we can write now is G4 particle definition. This is the class for our particle, and this object that we create is simply called particle, and then we can write here particle table, and the member function is now find particle. And let's suppose we want to create an electron, so a positron, so we can write here E+. So it finds this particle E+, creates a positron from that, and then hands it over to our particle class, particle object. So then we can write here F particle gun, and now we have to hand over everything to our particle gun. So we have to write here set particle, not polarization, but position. And there we have to hand over our G43 vector pos. And the same we have to do for the momentum. So we have to write here set particle momentum direction. This is our momentum vector. And the direction is of course not the only thing which we need, because we have a vector, we also need magnitude. So we can write here set particle energy, and here we can write 1 times GeV, giga electron volt. So this is a unit that we use in order to make sure that we have 1 giga electron volt. And then we can use here F particle gun, set particle charge is not important because this is already defined by having a positron. So now we can write set particle definition particle. So then we hand over our particle definition to that particle gun. And now we also have to define our destructor. But this is simple because the only thing which we have to do here, we have to delete our particle gun to make the memory free again. And then we have to finally write here PM primary generator, generate primaries, and again we have to take over our G4 event, and let's call that object just an event maybe. Then we can write here create vertex. So what actually happens is that our particle gun generates a primary vertex. So this is the function that shoots a particle, so to say, and we have to hand over our event to that. And yeah, this is everything what we have to do. Now our file is actually completed. Again, we can test it by writing CMake.dot. It is important to make sure that it finds all the C and header files again, and then we can make it and we don't receive any error message, which means that our program until now works very well. Now the only difference here compared to the other things that we have done before, we cannot hand this over directly to our main simulation file. We have to create a new class in order to take over this primary generator, and this is called action initialization. So what we will do now, we will create again in our include folder a new file which is called PM action initialization.hh, and here we include now include now, no, before we do this, of course, we have to define our, define our protection, PM action initialization underscore HH. And again, we can copy this definition and write here and if. And then what we have to include now is our G4 user, G4v user action initialization.h. So again, we take over the main class from Geant4, and we have to inherit from that in order to define our own user-defined class. Then a few things we need in addition, which is our PM primary generator HH, of course, because we need this. And yeah, this is, I think, everything what we actually have to include. Yes. So now we can define our class PM action initialization publicly from G4v user action initialization. And again, we have to define our constructor PM action initialization and our destructor, which can be written as that. And now we have to define two functions. These are virtual functions because we have to override the functions which are actually already implemented. So we can write now virtual void build for master. This includes everything which is handled by the master thread, so to say, because we have installed Geant4 in multi-threading mode. So we have to one function for the master thread, and then we have to define one function for the single threads, which would be virtual, or which we can just call virtual void build. And in both cases, they have to be constant. So we have to write const behind that. And then we need another semicolon to close our class here. This is, I think, everything that we need. Then we can go back to our source folder, and then we can create here a new file, which we call then accordingly PM action initialization.cc. And then the only thing which we have to do, again, as usual, we have to include our PM action initialization HH. And then we have to define again our constructor PM action initialization, PM action initialization, and similar to our destructor as usual, we don't have to implement anything here. Then we have to define our build for master function. So this will be then build for master. And here, for the time being, we don't need anything. Later we will fill more things into that, but for the time being, we can actually just simply avoid that. And then in the next step, we only need our PM action initialization our build function. And here we have to then hand over our primary generator. So we have to write PM primary generator and create an object from that generator. Let's call it like this. And then we can write here PM primary generator, and the constructor is empty. So now we can write here set user action, and then we can write here generator. Yeah, and as you can see, we can have two error messages here. So because we said before we declared it as constant, so we also have to, of course, write our const behind that. Yeah, but now it seems to be complete. Now the only last thing which we have to do, we have to go back to our main file, and then we have to write here in the same way how we implemented our physics list and our detector construction, then now we have to add our action initialization to our run manager. So we can write here, first we have to include it of course here as well. So we can write PM action initialization HH, and then we can write here PM action initialization. Okay, now in principle everything should be really completed, and we can write again CMake and make to check whether everything works well, but it seems to be fine. Yeah, and then the last thing which we have to do now, if we want to display anything, yeah, this is not exactly related to Geant4, but it's related to the visualization, and this is to tell Geant4 how the visualization will take place. So the only last thing which we have to do now is to create a visualization script. And once we have done this, we can use this in the future as often as we like. So in order not to put everything into our main folder, I would like to create another folder here, which I call macros. Maybe in the future we will create more macros, and I will explain you in detail what it means. But for the time being, we just have one file in this, and this we call vis.macro. Yeah? And in this file, we have to write run initialize, yeah, to initialize our Geant4 framework, so to say. And then we have to initialize our graphical output, our Qt window. So we have to write here vis open and then OpenGL 600 cross 600, which means 600 times 600 will be our window. And then we also have to write here -0 +0. And then we can create, or then we can set our viewer to a special view point. So we can write here set slash viewpoint vector 111. So now we look from 111 from the direction 111 into our volume, directly straight towards the origin of our coordinate system. Yeah, so now in the next step we can also define more parameters of our viewer. So what we can set here is for example auto refresh, true. Whenever something changes it will be automatically displayed. Then of course we also want to draw our volumes, so we can write here vis draw volume. This is important, otherwise it will be empty. And then I would like to add a few things to our scene to just make it everything more prominent and visible. So for example, we can add now to our scene trajectories. Otherwise they will not be shown, the trajectories of our particles that we shoot. And here we can write, for example, smooth. Later I will also show you a few more examples, but for the time being this is the best idea. Then what we can also do, we can write here vis scene end of event action accumulate. So it makes sure that if we shoot more than one particle, they all accumulate and we can see them in our viewer. So now with scene, what I usually like to add is a scale to check how large our volume is. So I would like to add a scale of 10 centimeter. And in addition, access to our coordinate system to check whether everything works well and our volumes are placed in the correct way. And the last thing which I would also like to add here is the event ID. So for every event we can see which ID it has. So then I think this is everything what we actually need. Now we only have to insert this back into our main file. So when we go to our UI manager, we can write here UI manager and then apply command. And then we have to hand over a string. which is control execute and vis.macro. Yeah, so it takes over the same commands that we can also use in our macro. We can also directly insert here as strings in our apply command function, but I would like to always separate this and to make it easier to understand. So in this case, we only use here the command control execute, and then we execute our visualization script. Okay, so now we only have to make sure that the file is copied to our build folder, because otherwise it will remain in our main folder, which does not help us at all. So we have to go to our CMakeLists.txt, and there we have to go maybe here below our source folder and write here file glob macro files, and then we hand over our wildcard for our macros. All macros which we'll create in the future will automatically be copied. And then we can write here file copy macro files destination, and then we write here CMake binary dir. Okay, and if we didn't do any mistake here, we can write CMake ... and then we can check in our build folder. Now, in addition to our make file and to our binary, we also have our vis.mac, which will be then later executed. Yeah, here in the visualization file, I also did a mistake. For scene, I had to also add right here add scale, yeah, similar to axis. Then once more we can write CMake ... and make, and then run our program. And then if everything works well, you can see this very nice Qt OpenGL window, and there you can see our coordinate system X, Y, Z, and you also see our world volume here. And then what you can do in addition, you can rotate that. You can also press Shift and shift it. Here you can also see our scale of 10 centimeter. And now you can press here this button, Run On, and it will show you that we are in run 0, and one event has been created. And this is a positron with our defined energy. And you can see the positron is positively charged, so it's blue. And then you can also see some delta electrons that are created here, because our positron interacts with air inside the mother volume. And we can create many of these by just clicking, and every time our run number increases, or we can just write simply run beam on, for example 100, and then we get 100 events created. And you can also see some multiple scattering. Yeah, the X position, X, Y, Z position of the particles slightly change. And then you can also see more of these delta electrons here are created. Yeah? And we will do many more experiments with that, and we will see later that what kind of nice things we can do. Now you can also see 100 events are shown here, and we are currently in run 25. Okay, this is everything what I want to show you today. It was a quite long video, but I think it was necessary to go through all these steps. And I hope that now you are perfectly prepared and you can play a little bit more with that. And with this, I would like to thank you very much for your attention. Hopefully see you soon for a new video. Thank you very much for watching this video. If you like the content and want to see more of it, please like and subscribe. And in addition, any kind of support is always appreciated.